This is the third example in a series of videos where we're looking at the titration of a weak acid with a strong base. In the previous two, we looked at what is the pH before we add any base, which is just calculating the pH of a weak acid. Then we looked at how do we determine the pH before the equivalence point, and that turns into just a stoichiometry problem and then a buffer problem. And in this third example, we're going to look at how do we calculate the pH when we're at the equivalence point. But just like the previous video, when we were before the equivalence point, and I'm assuming that you've already watched that video, it's a two-step problem. First, I do a stoichiometry problem involving the reaction of the strong base that we're adding to the weak acid. And then the second step is an equilibrium problem using what is left in the solution at the end of the reaction. And so I've built the same BCA table that we made in the previous slide. And of course, the initial moles of acid aren't changing in the titration. So I've gone ahead and put in the moles that we calculated in the last video. So to finish this off, I need to calculate how many moles of hydroxide I have. So to do that, I'll use that the moles are equal to the concentration times the volume. All right, so I can go ahead and plug that in for the hydroxide here. Let's try that again. And I don't care about the water. The concentration of the conjugate base is initially 0. In this case, the limiting reagent is essentially both of them. They're both 0.08. So it'll be plus that same value. So I'm left with no hydroxide at the end. I've got no weak acid. And all of the weak acid has been converted into its conjugate base. So when I look and see what do I have left at the end of the first reaction, so I have no strong base left over. I have no weak acid, so it's not a buffer. All I have is weak base left over. So essentially what the problem becomes now is just how do I calculate the pH of a weak base? And we know how to do that. But to calculate the pH of a weak base, I need to know its concentration, and this is its moles. So I need to get the concentration of NO2 minus. So to get that, I'll just do molarity is equal to moles over the volume. So I'll take the moles. Over the volume, but I need to be sure to use the total volume. So I started with 100 milliliters of acid. I added 160 milliliters of strong base, so my total volume is 260 milliliters, or 0.26 liters. All right, so when I do that calculation, I get, all right, and so we'll continue with this problem on the next slide. All right, so what the equilibrium problem boils down to now is I need to calculate the pH of 0.308 molar NO2 minus, which is a weak base. So the first thing I want to do is write down the chemical reaction. So I have NO2 minus reacting with water. NO2 minus is a weak base, so I'll need my equilibrium arrows. If it's a base, it's going to be a proton acceptor, so the products are going to be its conjugate acid and, it's conjugate acid and OH minus. All right, so this is an equilibrium problem, so I will call this an ice table. So the initial concentration of NO2 is 0.308. Don't care about the water. Those guys start out at 0, so I've got minus X, plus X, All right. Now, in order to do this calculation, I need to know the equilibrium constant. And I know the Ka of HNO2, but what I really need is the Kb of NO2 minus. So I'm going to use that the Kb of NO2 minus times the Ka of HNO2 is equal to 1 times 10 to the minus 14. So that means that the Kb of NO2 minus is 1 times 10 to the minus 14 divided by the Ka of HNO2. And so I get my Kb to be 2.17 times 10 to the minus 11. And so we'll finish up this problem on the last slide. So now it's just a matter of plugging in the values from the equilibrium row of my ice table into the equilibrium constant expression. So I know that Kb is equal to HNO2 times OH minus over NO2 minus. So this becomes Kb that we found last time. Of course, in this case, K is extremely small, so I can use the K small approximation. All right, so that means I can essentially ignore this minus x. So I'll just go ahead and erase them. All right, so I'll multiply both sides by 0.308. So I take the square root of both sides. So x comes out to be all right, and so remember the x from our ice table is the hydroxide ion concentration. So in order to get the pH, first I'll get the pOH, and then I can get the pH. And then I know that pH plus pOH is equal to 14. pH plus pOH is equal to 14. So pH is equal to 14 minus the pOH, or in our case, that's 14 minus 5.59. So our final answer is the pH is 8.41.